Hey there, it's Shannon Matrick Myers coming at you live from San Diego, where it actually might rain, amazingly enough. Today we'll be looking at valid and invalid arguments, a very important part in the art of mathematical proof. So let's get going. In math and logic, an argument is not a dispute. Doesn't have that negative connotation. It's a sequence of statements ending in a conclusion. Okay, so if red is a tiger, then red is a feline. Well, suppose this first part, call it a premise, is true. So if we say red is a tiger, therefore, red must be a feline, right? And that is definitely a true statement. Now think about it going the other direction. We're not going to go into it too much in depth right now, but we'll take a look at it a little bit later. So here, if we were to denote, or let P denote red as a tiger, and we can let Q denote red as a feline. So these three statements altogether are a valid argument form called modus ponens, which we'll learn about like in moments. All right, so in this case, what did we have? We had if P, then Q, right, as line one. Then we said that P was true, and so we said, therefore, Q. All right, so keep that in mind. So, definition: an argument is a series of statements and an argument form is like what we just talked about. That argument form was a form called modus ponens, all right? So an argument form is a sequence of statement forms. All statements in an argument and all statement forms in an argument form, except for the final one, are called premises. They are also called assumptions, or hypotheses. The final statement or statement form is called the conclusion. The symbol, this kind of triangle of dots, is read therefore, is normally placed just before the conclusion. But sometimes, there's like many conclusions until the final one. So it doesn't mean you'll just see it once, all right, in your work. All right, so to say that an argument form is valid means that no matter what particular statements are substituted for the statement variables and its premises, or premises, I guess, if the resulting premises are all true, then the conclusion is also true. To say that an argument is valid means that its form is valid. All right, so from our example before, let's take a look at the truth table. Remember, we had this situation. Hang on, I'll just copy it. And recall that what was our whole format? We had P implies Q, P, therefore, Q, right? Now, let's check out the truth table, your very favorite thing to do. So if we make our truth table, we would have, all right, so the way I set it up, this truth table up, is I have, just the regular P and Q, and then I have P implies Q, and then I have the conclusion Q. So that'll just be kind of a repeat, but it can be a little easier to keep track of, all right? So here we go. I'm going to put our premises in a different color this time. That will be important for us. And so isn't P one of the premises? I mean, both of these are premises, okay? So P can take on values of, why did it get so giant here? All right, so P can take on values of, we'll just go down true, true, and then false, false. All right, Q is our, for now I'm just going to write it in this regular color. So Q would, So Q is true, false, true, false. I'm sorry, this kind of came off a little bit. All right, so P implies Q is another premise, is it not? So we'll write this one in pink as well. So P implies true. Remember, the only time it is false is when what? Awesome, you have a false conclusion and a true premise. So this will be true. This guy will be false. Then we'll have true, true. I'm going to rewrite Q in a different color. This will be like the conclusion color, all right? And I'm only going to look at the lines where both of my premises are true. This is what the last definition was speaking to. So you only have to check that the ones that both have trues, okay? It's called a critical row. So you need to make sure that your conclusion statement or statement form is not false, all right? Because if it is, then you won't have a valid argument. So let's check it out. Q, remember, was true here. And so we have a true, and a true. We're good to go, all right? And that is the only spot where our premises were both true. Do you see the other ones? We've got a true, false, a false, true, and a false, true, looking at the pink ones. So we're good to go. This is a valid argument, okay? And we'll speak a little more to this as we return. And again, this was called, this type of argument form is called modus ponens. All right. The takeaway. A valid argument is one in which the truth of its conclusion follows inescapably. From the truth of its premises. It's impossible to have a valid argument with true premises and a false conclusion. That's a lot of the reasoning we were just using. When an argument is valid, and its premises are true, the truth of the conclusion is said to be inferred or deduced from the truth of its premises. If a conclusion does not necessarily follow from its premises, then it isn't a valid deduction. Okay, so what did we do in this last one? I mean, if you want to write some steps onto testing an argument for validity, right? Well, what did we do? We identified the premises and conclusion of the argument. So in the one we just did, remember we did the premises in the kind of purpley pink color, and then this here was our conclusion, was the Q here, this line. All right, and then what did we do next? We constructed a truth table, right? Showing the truth values of all the premises and the conclusion. Now, a row of the truth table in which all the premises are true, what did I call that? Do you remember? Is called a critical row. Very important. If there is a critical row in which the premises, in which the conclusion is false, then it is possible for an argument of the given form to have true premises and a false conclusion, which we said that couldn't happen, right? So the argument form is invalid when that happens. If the conclusion in every critical row is true, then the argument form is valid. So in that last example, we only had one critical row. Our critical row was here because this here is true. This is true. Those are both premises. And then we verified that our conclusion was also true. The other rows, right, where we have the purpley pink writing, they're not both trues. So we don't even have to deal with those. We just look at the critical rows, all right? Okay, so modus ponens we talked about a little bit, and modus tollens. So let's do it. An argument form consisting of just two premises and a conclusion is called a syllogism. I hope I'm pronouncing that right. The first and second premises are called the major and minor premise, respectively. So, modus ponens is going to have the form if P then Q, right? Or if something then something. this first one is true, so the way I've written it, P is true, therefore Q. That's a modus ponens argument. Now, a modus tollens has the form P implies Q, not Q, therefore not P, right? So these are two very, useful argument forms. Okay, so far? All right. So now you might want to make kind of a list of these forms that we're going over. This is all going to be pretty important, right? So let's do it. This first example, let's use modus ponens or modus tollens to fill in the blanks of the following arguments so that they become valid inferences. If a phone is an iPhone, then the phone is an Apple product. The phone is an iPhone. So what's our major premise? Perfect. The phone is an iPhone. What's our minor premise? The phone is an Apple product, right? So the major premise is true, and to make this become a valid inference using modus ponens, we would say, therefore, the phone is an Apple product. Okay, so if 7 is even, then it is divisible by 2. Well, is that true? Do you think that's true? Not unless you've been drinking, right? So 7 is not divisible by 2. We've negated that, right? We've negated the minor premise. Therefore, 7 is not even. Cool, cool? All right, so here's a bunch of additional valid argument forms. So rules of inference. A rule of inference is a form of argument that is valid. So the modus ponens, the modus tollens, those are both examples of rules of inference. Now, let's just look at these different formats. Generalization, that's a certain technique, okay? Jill rides her bike to work. Therefore, Jill rides her bike to work, or Jill rides her bike to the bar, right? You can make some generalization like that. So in symbolic form, it starts out with P, and then you get, therefore, P or Q. And the reason why we can do this is because, beautiful, when you have an or statement, only one of them needs to be true, and you already know that P is. All right, it's the major premise. You can also say Q, therefore, P or Q for the same reasoning. Groovy? All right, so specialization. Actually, I'm going to be more mindful of my space here. In specialization, the figure is a square and a rectangle. Therefore, the figure is a square. All right? So, here we go. You've been given that this and statement, right? So your major premise is the figure is a square, right? So this could be like RP. And then the minor premise is that the figure is a rectangle, right? And you're concluding that the figure is a square. And so what you do is this. You've been given P and Q, right? And from this, we're going to say then P, or therefore P. You could also say P and Q, therefore Q. So that is if you need to come up with, this variable for some reason, or this argument form for some reason. What'll happen is you can kind of create one through specialization. Okay, elimination. Shannon teaches at MiraCosta College or Southwestern College. Shannon does not teach at Southwestern College. Therefore, Shannon teaches at MiraCosta College. Well, here we have this or statement, right? So in this or statement, if this is our major premise, Shannon teaches at MiraCosta College, and this is our minor premise, Shannon teaches at Southwestern College, we've been given the negation of teaching at Southwestern College. So what format do we have? We have a P or Q. We've been given, not Q, right? So what do we conclude? Therefore, P, because it's got to be one or the other. You can also do it the other way. You can say P or Q, not P, therefore Q. All right? Alrighty, transitivity. If red is a tiger, then red is a feline. So with this one, if we let, red being a tiger be P, red being a feline could be Q, then we'd have Q, and red being a cat could be R, right? So, okay, what are we saying? An if-then statement, and that's P implies Q, right? Well, the second line is saying that Q, if red is a feline, then red is a cat. So Q implies R. Well, going with transitivity, we would have therefore P also implies R. Okay? And then if we go into division by cases, red is a tiger or a house cat, right? This could be our P, this could be our Q. If red is a tiger, then red is a feline. Well, so if P, then what? Some other R, some other thing. If red is a house cat, now we're back to Q, then red is a feline, right? So which one was red is a feline? That was R. Therefore, red is a feline, therefore R. Okay? So let's check it out. This said that red is a tiger or a house cat. So we would have P or Q. If red is a tiger, then red is a feline. So that would be P implies R. If red is a house cat, so that was Q, then red is a feline. So that implies R. Therefore, R. All right, and that one's called proof by division into cases. So we'll have examples of all these, don't worry. Fallacies, converse error. All right, so if red is a tiger, then red is a feline. You're probably tired of red. He's one of my cats, by the way. He has a starring role, and he thinks he's a tiger, which is why I said initially he's a tiger, not a house cat. So if red is a tiger, then red is a feline. Well, red is a feline, therefore red is a tiger. Are all felines tigers? No, right? Jaguars are felines, lions are felines, all that good stuff. There's different formats here. So here we go. PQ, right? And you can't assume what you're trying to prove. This is the mistake of, it's called converse error, and it's the mistake of assuming what you're trying to prove. And this is very common. People do this quite a bit. Okay, inverse error, on the other hand, is, so remember that P implies Q, assuming Q isn't going to work. This is a bad argument. Now, inverse error is saying that if you negate the major premise, right, then you can negate the minor premise, and that does not work either. So here, this is an example of inverse error. If red is a tiger, then red is a feline. Red is not a tiger, therefore red is not a feline. I mean, you can see that that argument doesn't hold water, I hope. Okay, so let's look at our example 2. What's wrong with this picture? If Violetta is a teacher at Maricosta College, then Violetta teaches math. Violetta is not a math teacher, therefore Violetta is not a teacher at Maricosta College. What kind of error is this? Aren't these things, both statements, right? But just because Violetta doesn't teach math doesn't mean you can negate that she's a teacher at Maricosta College. We've got all kinds of different subjects we teach, right? So this is an example of inverse error. If red is a tiger, then red is a feline. This is from our first one. Red is a feline, therefore red is a tiger. So do you see that just because red's a feline doesn't mean he's a tiger? So the converse is only true if you have that stronger if and only if statement, right? So this is converse error. Definition: an argument is called sound if and only if it is valid and all its premises are true. Sorry, I'm missing a word here. An argument that is not sound is called unsound. Contradictions and valid arguments. Suppose P is a statement whose truth you want to deduce. In mathematical proofs, one powerful tool is the contradiction rule, which is applied by supposing that a statement is false. If this leads logically to a contradiction, then you can conclude that the statement is true. Right? So let's take a look at this example. Please use truth tables to determine whether the following argument form is valid, right? So here we go. We're going to need a few things. So why don't you go ahead and make the truth table and do all these things, and then come check on back and see how you did, all right? all, hopefully you got the same values that I did. We have how many critical rows? Beautiful. Here we have this one here because they're all true. These are all true and these are all true, and it's the premises, right, that are all true. So all of these here are the premises. And then our conclusion, remember, was just the not are. So we need to examine in the critical rows, what are the values here? So we've got a true, a false, and a true, right? So what that means is that even though it was just this one part of the whole thing, it deconstructs the whole argument, right? So this argument form is not valid after all that. So this argument form, meaning this stuff here, right? Okay, so here we go. Let's take a look at this example here. It's kind of a fun one. Which dog stole the tri-tip off the kitchen counter? Shasti, Einstein, Rango, and Bonnie, the dogs, are being questioned by Billy. Billy determined that all of them were lying except for one. So we need to figure out, who is telling the truth. And then from that, we'll be able to figure out, who did it. So Shasti says Rango did it. Rango says Bonnie and Einstein were playing ball outside when the tri-tip was taken. Einstein said Bonnie didn't do it. And Bonnie says Rango didn't do it. Good so far? All right, so I don't know if you want to do this in symbols or not. If we let each letter of the first name denote that dog is telling the truth, we would have S means Shasti is telling the truth. And then R means Rango is telling the truth. And those, tick marks mean those are the same words. E will mean that Einstein's telling the truth. And B means Bonnie's telling the truth. Cool so far? So, suppose that Shasti is telling the truth. All right? So suppose S. That means suppose Shasti's telling the truth. Well, if Shasti's telling the truth, Shasti said that Rango did it. And if you read through these statements, premise B is Rango saying something about Bonnie and Einstein, but nothing about himself. So that one's not going to affect us. But premise C, Einstein said Bonnie didn't do it. Well, if Shasti told the truth that Rango did it, then Einstein would also be telling the truth, right? But isn't that a contradiction? So what we get from that statement is this, right? So now we know that Shasti is lying. So therefore, we have not S. Shasti's not telling the truth, right? Well, what would not S imply? Not S would imply that Bonnie's telling the truth, right? Because Bonnie's saying that Rango didn't do it. That makes sense? So if Bonnie is telling the truth, right? What does that mean? It means all the other ones are lying. So Bonnie telling the truth means we have B implies not R. B implies not E, right? Well, if Einstein's lying, Einstein said that Bonnie didn't do it, right? And if Rango's lying, that means he didn't really see both Bonnie and Einstein playing ball, right? Outside. So what conclusion do we logically come to? Bonnie took the tri-tip. She's the tallest one anyway, so. All right. So that's, kind of a harder one to reason through. But, that's okay. You just take it in pieces and just do the best you can. All right. Just go slow and no freaking out. All right. So this last example, A, B, C, D, E, F, these are all premises, right? And so we're going to go ahead and we're going to use the valid argument forms that we learned today to deduce the conclusion from the premises, giving a reason for each step. And so we may or may not be going in order here. It just depends on what happens, right? So the very first thing to look at, look through all these conditions. Yes, P or Q, we could definitely, do, I don't know, kind of a conjoining kind of thing, or we could definitely do an elimination, but that's not going to help us, right? Because we don't know which one to eliminate. So let's take a look at premise B, right? We know that Q implies R. These are assumed to be true, right? And that one is from premise B. I'm just going to say B if that's okay. So that'll be from B. It's given in the statement. All right then, well, Q implies R. If we were to say, what else could we use? Beautiful. We could use another premise that says not R, right? What premise was that? Awesome. Premise D. Well, by modus tollens, right? What would we then have? Good. Therefore, not Q, right? You negate that second premise, the minor premise, then your major and you use modus tollens, then your major premise would be true. Or not true, sorry, not true. Okay, so now we've established not Q. Alrighty, well, let's take a look at the next thing we can do. So we've utilized B. I mean, I don't think we'll have a use for it, but we'll just keep it. We won't scratch it out. So now that we've done that one, what else could we do? We know it's not Q. So wouldn't it be kind of nice to simplify premise A? We know that it's P or Q, right? From premise A. But what did we just find out? We just showed that it's not Q. So you would just put number 1 for that first part. You know, we're dividing this into cases. And so that's our proof. Well, what's that one rule? There's that elimination rule. We want to, get to the nitty-gritty here, so we can eliminate Q from the P or Q statement because we know that we have a not Q. So, therefore, P. Groovy? All right. Next up, let's see what we got. So this one from premise E, not Q, implies U and S. So that's premise B, or premise C. No, E. All right, so let's check it out. We have, I know it looks more complicated, but do you see that we have something implying something else, right? We also know by equation number 1 that not Q is true, right? So that was from equation number 1. Well, by modus ponens, do you see what would we get? We didn't really, I know it's a negation, but we didn't negate that second one, right? So it follows the modus ponens. And so for the modus ponens, what we would get then is therefore U and S. All right. Okay, moving along. Don't you just love proofs? I do. Now let's look at what we just worked on. We know we have U and S. That's from number 3 here, case 3. So from this, what can we do? I mean, if it's an and statement, don't both of them have to be in there? Well, we're not really using U anywhere else, are we? But we do use S in premise C. So that specialization rule of inference means that we can say therefore S. All right, we're getting there. Now let's lay out some other stuff that we've learned. So we'll come up here. So number 5, or part 5, we know S is there from equation 4. We know P, and remember premise C, we're going to have to take care of that. So why don't we get P and S kind of on the record so we could conjoin them. So P, that comes from part 2. And then we got beautiful S from part 4. So what can we conclude from that? Whew. We can conclude, therefore, awesome, P and S. and that's from conjunction. All right, we're almost there. For number 6, we're finally going to go to premise C. So P and S implies T. And then P and S implies T. Well, what should we do with this? What do you think? We've got one thing implies something else, right? Do we know anything else? What did we learn from 5? Awesome. We learned that P and S is given as a premise from that last conclusion. All right. And so that gives us, that's from number 5. And so using, beautiful, the modus ponens, we'll get our conclusion of T. Wasn't that fun? All right, well, you have a wonderful morning, afternoon, or evening whenever you're watching this awesome video. And if you like what I'm doing, please subscribe, and you can always email requests for videos. I'll do that in all my spare time. All right, have a wonderful, wonderful day. Bye.